All right, that gives us plenty of opportunity for tech failures while the first speaker sets up his talk. I'm very happy to welcome on stage Yaroslav Halchenko. Yarik has traveled from the US, one of the founding fathers of DataLad, and just to give a little bit of motivation for those people who haven't just to give a little bit of motivation to people. So when you registered as a speaker, we ask you to provide a biography. And this is the biography that we get to welcome you on stage and introduce you to the crowd. And I will proudly do so. And maybe you want to update your biography after hearing how I introduced Yaroslav, because his biography didn't exist. And then kaboom, I'm here. And with that, a warm round of applause for Yarik.
Which was factually correct, right? So that's what I strive to achieve, to provide truth and only truth. So you must believe what I am just about to say then. Okay, let's see if it still works. There was a blink. Okay, at least you could see what's happening there. That's good. Okay. Let's replace it with this window, maybe. And then I'll make it full screen. And then I'll go here. Okay. Here we go. Hi. So my name is Yarik, and I come from you with Kaboom, from a land of Dartmouth College, which is in Vermont in the United States of America, where I lead Center for Open Neuroscience at Psychology and Brain Sciences Department. And there, with Michael and others, we work on a variety of projects. Some of those I link in the bottom. So this is QR code to the slides, if you want to follow them on your laptop or look at them later on, or explore any of the projects which are mentioned throughout this talk. And I strive to provide links whenever I mention anything so you could follow on your leisure. Okay, so let's begin, and we'll talk today about YODA, or to say more how YODA principles appeared and how they could be used pragmatically, and maybe some of you haven't heard, or who has heard about YODA principles? Oh, everybody, okay, I didn't have to talk. That's unfortunate, but okay, so the slogan would be YODA acknowledgements, right? So I acknowledge all the funders. Lots of work was funded. Original DataLad was funded through NSF and BMBF, and NIH funds lots of projects. But also I want to acknowledge that all those wonderful people from our DataLad working group, I would say, or DataLad project and Center for Open Neuroscience who assisted in preparation of this talk. So the slogan for this talk is YODA principle a day keeps gray hair at bay. And I stole it somewhat from my kid's poster. Her poster was a Tylenol a day keeps death rate at bay. She was studying C. elegans and Tylenol influence on them. So we won't go into medicine today. We'll talk just about YODA. Okay, and YODA came up to us in 2018. We prepared a poster for OHBM conference where we've tried to kind of instill best practices, how people should work with DataLad, but we've tried to make them agnostic of DataLad. And overall, they consist of 3 principles, right? So its first one is version control systems, and I reordered from original poster. So if you look and something doesn't match up, just change the order. And second one, that computational environments should be provided as well, and that you need to structure elements so it becomes modular and stays modular. And so they become relocatable and also within context and outside of context of your study. So we have all those materials on GitHub if you want to look at the original poster. So let's go through those principles. First principle is version control everything. And as you can already probably you do with DataLad or Git and git-annex, you could put anything into DataLad, whatever you have in a file, right? So you could put your input data, custom code, or entire computational environments. And that was kind of the main benefit from providing DataLad, that you could use the same version control system for all of them. And I'll reuse the same slide from last year. Why version control? Why do we version control? most of the time, and that's kind of underemphasized, that we use to collaborate, right? So we use all those version control systems to work together. I remember with Michael, I go to sleep, pass on the baton, I push everything to SVN back then. He comes in, he works, and then I fetch all the results. So we collaborated through version control systems even before Git existed. And it's useful to keep things synchronized, right? Many people use it that way, and that's how, let's say, assistant mode in git-annex was born, right? For providing Dropbox-like automation where you synchronize your files across different computers. And it's really useful mode when you're acquiring the data and need to channel it through different infrastructure. I'm not talking about it in this talk, but it's really important feature of version control systems, especially distributed ones. And of course, keep track of changes, use it as a backup, which is useful. And I really love grep functionality. I use it probably most of the, besides commit, right? Git grep is my friend, because it limits me to grepping only through the files which are under version control system, so it doesn't go through all the other junk, right? And because it's annex files are just symlinks, right? It goes only through that content, and you don't need, you could be in a huge repository with lots of data files, they'll be ignored automatically for you, kind of. So it's really useful feature. If you don't use that, that's great. But what I wanted to mention is that version control systems allow you to experiment, and that is really underappreciated kind of feature of them. And most likely one is when you plan for it, right? So you create a branch and you check it out. Then you work in that branch and you either merge it or you just discard it. And you could experiment multitude ways like that. And there is actually systems which are built on top of that, right? So people create branches for exploring different models when they look through the models. And another feature which came more recently, although it's been there for years, is work trees, where instead of just branches, which are kind of ephemeral in your .git, right, and you could check out one at a time, you could use work trees. And I don't remember, in git-annex it was also supported for a while already, work trees, right? So you could now quickly create a work tree for your even heavy collection of data, right? And it's really, really opens opportunities for you to experiment, right? Again, try different models, different preprocessing. You commit in that branch, and you have separate work trees. I will not talk about even AI and all the parallel explorations you could do. It just opens those opportunities to experiment. And there is unplanned experiments, which hopefully some of you are not afraid of doing all the time. This is what I do quite often. You tried something, right? And then when you're ready to do it clean, you just git reset hard, right? Git clean, and you do it clean now, right? Maybe with DataLad run, which I'll talk later. Or you could forget what you did, right? So you could go to the previous commit really easy with git reset -- hard. It's really a feature which is underappreciated and underused, I think. And there is overall time machine, right? You could jump in Git history with this git reset hard to any commit-ish, and it's amazing. People are afraid of it, but who remembers what Git stands for or how it's described in the man page?
Stupid content tracker.
Here we go. It's just a stupid thing, It just tracks your content, and you could jump inside of that content checkout space, right? Git checksums really easily, and that's your kind of mechanism for that. So don't be afraid to experiment, and tools are there. Okay, so we know that with Git and git-annex we could do tracking of code, all of that, we talked about it. But what DataLad introduced also on top is that functionality, which also present, I believe, in DVC, is to compute something and commit results of the compute. And that's kind of its really simple feature, and DataLad run implementation is really basic, right? It just verifies that, and we'll talk about DataLad run. The point is that with Git, we have now functionality. I just talked that we could git reset, we could experiment. Now we can, if we compute anything, if you have any computable change, you can use Git to do this help for you, right? So here, unfortunately, AI now refuses to make any complicated figure where I said draw me an alien who does brain extraction. It said, oh no, I cannot do that. That's really dangerous, right? So, but in neuroimaging, we always do brain extraction where you get rid of skull, right? So this is demonstration where you do DataLad run, and instead of doing just the command invocation, which would be here, brain extraction on these input files, you just wrap it up with DataLad run. And optional provide inputs and outputs specification. And what it does, it obtains all the data which is necessary to do, right? Because you specified in inputs, it will call DataLad get. And then it unlocks all the outputs if they're present, computes, and does the commit for you. And as a result, you'll get this nice commit message where you have a record that you've done this command on these inputs, and these were the outputs. So now, you know how you've got to this state, right? So stupid content tracker, right? So you know how you've got to that state, and you didn't have to explain in your commit message which command you ran, right? And later on, when you get in history, you know how you've got there, right? And this is really simple, right? You just provide it, instead of just running command, you said DataLad run that. So that's what I've got into a habit of doing all the time, and that's one of those skills which I think everybody should learn, that if you compute anything, if you run any scripting, don't just run the script and then provide your humble human explanation how you've got there. Just do DataLad run on that script, and you'll get this nice commit message. It will also ensure that you start from clean state. If you have something uncommitted, that state is kind of unknown, right? Because then later you wouldn't be able to reproduce it potentially. So then you have no surprises, right? So it's like, it helps you to go through your history with what is it, effect of least surprise, right? So you discover everything. And pretty much how YODA would have said it, how you got here, now you know, you do, right? You know how you got here, no, you do. Here we go, right? So you do know how you've got here, right? So you look through a Git history and you look, oh, this is what I've ran. And we use it all the time. We use it so much that we also sometimes redo it, right? So there is DataLad rerun, where you could rerun those commits and ensure, let's say, that it's all the same, right? And I call it also, it's functional cherry picking. So imagine now that in Git you use cherry pick, right? Which takes your patch and applies it as is to your potentially other state, right? But if that commit was the functional commit where you've ran the command, let's say you replace all words DataLad with, I don't know, just git-annex, right? Now, if you're applying it to another state, all your patches, first of all, might conflict, right? But also they might be insufficient because maybe you introduce some other word DataLad somewhere, right? But if you apply it functionally, you know that command which was set, replace, all that, right? Then it will be functional patch. And that's what I'm trying to introduce now in bits. Let's say we have PR where we would replace all participants TSV with subjects TSV. So I have that command which will provide functional patching. And you could do that with DataLad rerun. You could rerun your history not only for verification like in this case, but you could rerun it to another spot, onto another commit, and you'll apply it with those functional patches. Okay. And last year we talked about, also presented DataLad registry, which I will not talk much about it, and you are welcome to review that distributes talk from last year Isaac gave. But a little update, because Joey was interested, oh, how many git-annex repositories, how much data we are covering. So it seems to me we are about a 2 petabytes range, getting there, and this is not complete. This is what only we automatically discovered on GitHub and other portals, right? But why I mentioned it, because there I could go through that registry and check how many DataLad run commands I found. So I find it in about 14% of the repositories. Probably most of them are my code spell contributions to the world, you know, but some of them are not. So people besides me use DataLad run, and so should you. And if you think that you could trust Joey saying that a git-annex complete, it is not, right? Because that's what YODA did to git-annex, right? Now, there is in git-annex, and that's the beauty of our meeting last year, right? some ideas were exchanged, and now we have git-annex add computed, where you have a backend where you could assign how to get this file based on the commands. So in our case, we had DataLad run backend, I believe, as well, where we've tried to use those DataLad run commands, and that might work. But now there is built-in functionality in git-annex to afford something like that, and you could assign for these files how to get them computed instead of just fetch from the from some other backend checksum based. Okay, and with this DataLad run, we're already capturing inputs, outputs, record them, and what was missing piece is really important, I think, in scientific context. If you do it, we just print standard output and standard error into your face, and otherwise it disappears. So we, since then, created a little tool called Conduct. Con, because all the projects which we start in our Center for Open Neuroscience need to start with con. So it's Conduct tool, and if you use duct on command line prepended to your command, it's stupid tool. It just captures all the standard out and standard error and puts into a file, but also it samples your process so you know about CPU and memory consumption. So later on, if you are to schedule it for HPC, you have statistics, how much resources you need to allocate. And here is a little bit screwed up example, especially on this display, where we modify our .datalad config for container execution, which I'll talk shortly after, and where we just added duct in the front. And when we've ran now, and by default, now if you just set this environment variable with our repronym containers, it will do it for you. And then, besides only running and committing, you could see that there is summary from duct, that it took so long to run, and this is where you could find all the output files, and this is peak CPU usage, right? In this case, it was like 6,000% or something. And we create these records in JSON, so you could easily read it with your tools, how much memory CPU was taken at those time points. And at the end, we also commit all the standard out and standard error for you. So you could take those and use conduct plot, and plot also nice graphs. This is kind of idea we took. It's not groundbreaking, but it's this modular architecture. Now you have this tool you could use with DataLad or without to track execution and know how much resources you needed. And we have duct gallery, so if you have some cute demonstrations, you captured something for, I know, bug reporting or something, and they look cool, contribute them here. So this Git repository where you could just push those traces and we'll create rendering for it on the web. And overall, so what we achieved, now we have version control everything, right? So we indeed captured all the data, we captured execution with DataLad run, we captured even standard out, standard error, we captured statistics, how long it runs, so it becomes really nice collection of resources for us to go forward. And you could experiment and embed those actionable items into your Git history. And why we're doing that overall, right? I think it's like for a life pain balance, right? Because later on, you know, what we typically encounter, we get to some repository trying to do something, and apparently we depended on something untracked, right? So, and you know, that's the pains we are going through, and that's what we are trying to eliminate. We don't want to depend on untracked files. So this is what Austin gave me when I asked him about what you think about don't look up, and we'll get back to it later on. So learn control you must, people. This is YODA's advice, and we could go to YODA principle 2, which is portable compute environments. About those, many people probably know, right? So we have many obstacles with software, right? Sometimes it's hard to deploy, and it's harder on shared systems. We have many solutions which emerged through the years, right? So it's much better now, but still those hurdles exist. Sometimes we cannot just install them because of conflicts, and different versions could produce different results. This is what we encounter in neuroimaging. I don't know if that's the case in your domain, but most likely so. And what is solution kind of permeated through the field is software containers, because they're easy, cheap, and they encapsulate your entire software environment, and they could potentially isolate from, you know, all other disk space, even network if you want, or GPU. depending on containerization technology. And there is two families. Most of you probably know about them, but these could be useful links for others. Docker and Podman, which is kind of initial containerization technologies, and then Singularity and Obtainer, which were created specifically for HPC. And by the way, Singularity Hub, it's kind of gone. Vanessa stopped maintaining it, but it's managed as DataLad dataset on our resources. So if you pull anything from shop column, it comes from DataLad. How cool is that, right? And you could get all of those containers from our datasets at datalad.org. And to manage those, we have DataLad container extension, which assists to add them in, and you could add it optionally to your DataLad installation. And then, because for DataLad containers are just another file, right? It all goes in, and you have your containers in there. And .dataLad config is where specification is how to execute them. Based on that, we created Repronim containers collection, where we took all neuroimaging containers relevant in the field and put them in the single reusable data set, which serves as a backup. So you could easily get this backup and keep it on your infrastructure. So if Docker Hub disappears or they remove some important containers, you have your own copy, or we have it for the whole field. So I would advise you to create something like that in your field or contribute to this collection. And we are working also to accompany it with open container images in addition to Singularity. With that, instead of DataLad run, you could do containers run. And then you have everything encapsulated and inside your commit messages, where it would look like this. This is example from recently computed by Felix, MRI-QC on neuroimaging dataset. You could see that you have everything necessary to reproduce that. You have access to the data through git-annex, you have the command, and it becomes much better, right? Portable compute environments, they allow us to reuse, exact version, you have availability and accessibility to those now and in the future. Unlike others, if they don't do this YODA version control system, they might be gone from the hub, right? So use DataLad and your version control systems to contain all of them. So depend on where you run, you should not, right? So with those containers, you could run compute anywhere. And the last principle is this modular composition, which kind of anyway in our life, we already use modules, right? In Python, even module, what is it? It's a file, right? It modularizes, brings together common functions. Then we put those files into directories. That's another level of modularization, right? And then we take different files, put them into software packages, right? And containers contain different packages. So we have those modules in our life, and we modularize them already. And what's important is that they all establish some kind of grouping, but also transformation, right? So typically we don't know how we've got there. We don't know why we copied files into that directories or where from, right? But there is transformation, and we freeze the state. So software package is a frozen state of compilation from specific sources, right? So we compile them, and now we use them in most convenient fashion, right? We have binary package, which deliver, and people use it, right? So this frozen state is really kind of useful concept. And we have other organizations which are global, right? So our file system on Linux is global organization, but it's not under our control. And let's say how configuration for X and other desktops organized is also global, and it's kind of spread around. And that's why typically packages are managed centrally through some package authority to distribute the content through this global space. But what we want really is that we want local organizations, and we have them. All Python projects organized similarly. So in YODA, we proposed, okay, let's propose some organization where we have files organized in consistent fashion. And now we have similar ones everywhere. And we propose also, let's say, in your domain, if you have some standard which tells you how to organize files, in our case it's bits, brain imaging data structure, you could organize all your studies the same way. And this is the transformations which we go through all of them. How could we do it in DataLad land? It's with Git submodules, we could provide this organization which scales up. Who uses Git submodules daily basis? See only a few people, or you just sleep in there. Okay, so Git submodules are really powerful. It allows you to install on demand. I'll stop shortly. And there is different decision points how and when do we need to modularize. And this is one of the lists, and I promise that there will be a pointer to benchmark on file systems. If your interactions with git-annex are slow, you might want to consider different file system, and this is the pointer to all benchmarks. So check it out. And those Git submodule scale, the data says that DataLad work is proof that it does. We have over 8,000 submodules up to 6 levels deep, and it's all manageable, right? So it's all manageable, and you could achieve this all YODA all the way down, right? So pretty much, you could have all your study, which goes from the paper to analysis to pre-processing to raw data through these Git submodules, and all of them are YODified. And then this is typical workflow from reproducible containers, which outlines that you create a result and then you install all the necessary components, you use DataLad run or containers run, and you achieve your reproducible results, right? So again, with those DataLad run commits. And there is alternatives, let's say repro one presented by Joe last year. Again, link to the talk. And this way, all OpenNeuroDerivatives are structured that you have all of those pointing to the source containers and reproducible containers I mentioned, raw data, and other components as submodules, and then capturing all the outputs and having a record of all the commands for batch system. And pretty much you obtain all those results, and what is the common principle behind all of them? I've mentioned already the code name. Look up, you must not. So YODA principle is that you must rely only on the content which is reachable within hierarchy of your folder, right? So you produce most of your own content, but why? You would ask why. And the answer is the same, right? It's like you must not depend on untracked files. And if it's upstairs, you don't track it. You don't know what it is, right? So you might end up in a situation that you depend on something which is not under your control. So in this kind of scenario, when preparing pre-processing, you must not depend on something which sticks out and lives outside. So corollaries from that, all related content could be version controlled, we know that. Containers, then if you use that approach, then you need to bind mount on the current folder. It's like, who experienced all this container specification? It's like, oh, mount this from there, in there. So you have all of those problems with explaining to human being, how this mapping happens. But if you bind mount current directory, and that's it, you have it all. Take home message. More on YODA via DataLad, and there is pointers. We have wonderful handbook Michael and Adina created. And DataLad or not, you could keep it all in VCS. And thank you. Follow YODA, and it will be efficiency and reproducibility.